All right, we'll keep on working with matrices and how to represent data and specifically linear regression using matrix notation. So we'll go ahead and work with the appliance stored data. It is a simple data set. It is simple linear regression. So we'll see how it works. So let's just write this appliance store data and matrix representation. Okay, so first of all, let's create an object um, that contains the y variable, and that is the y vector. So let's say y vector here. And remember how we just get vectors to be represented. So I can just say y is equal to, I would use the matrix constructor, and using the concatenate function, I will just put the values that I have on the y variable, 1, 1, 2, 2, and 4. I just need to say that the number of columns is equal to 1, and that would be enough for me to represent the y vector. Um, so again, the y vector, you can see it here. If you type it on the console, it is a one column vector, and that is enough to be representing that particular example. So now let's create the design matrix. There's multiple ways to do it. For now, we'll just do it um, everything at a time. So remember that the design matrix needs the first column is a column of ones, and it's going to have the same number as the observations. So it's the same number of ones as the observations, and then we would have to input every single predictor by itself. So then every predictor. All right, so let's call it X. This is a matrix, so we'll use the matrix constructor. We'll input first the column of ones, so that means that we need 5 values of 1, and then we will input the numbers on the predictor, which is advertising expenditure that you can see here. And that would be 1, 2, 3, 4, and 5. I just need to tell um, the constructor that I even, if I want to just say that I have 5 rows, I can say n row is equal to 5, or I can say n column is equal to 2, and that would be enough. Again, that's the main reason why we need to understand the dimensions of the matrix. Again, let me show you what the design matrix X is. We have a column of ones, and then we have a column of the predictor variable. Okay, so that is the design matrix. Now, to obtain the parameter estimates, there is um, a formula that, again, you don't need to remember that formula, but I just wanted to show you that on the background, um, the parameter estimates are calculated using this formula, x transpose x, and then I take the inverse of that, and then x transpose y. So that's how I would obtain the estimates of the parameters. That formula is guaranteed um, to obtain the lowest SSE on this regression, and again, guaranteed to obtain the lowest SSE for any other linear model. Again, we are assuming that the data behaves linearly, so that is linearly related to each one of the predictors. So let's go ahead and do these. If you want to do it at the same time, um, calculate the whole formula at the same time, that's fine. Or if you want to just do these one step at a time, so for instance, you can say let's get first x transpose x. So let's call it xtx. And I can just say this is equal to the transpose of x. Remember, the transpose of x is calculated using t of x. And then I need to multiply that times, remember, this is the notation used for matrix multiplication, times x. So remember, this is guaranteed to be conformable for multiplication because this transpose, we're transposing a matrix and multiplying it by the same matrix. So that would be x transpose x. Let's look at it. And we see here the values of x transpose x. If you, the only reason why we have this slide right here is to show you what x transpose x is composed of. The value on the top, in the upper corner here is the number of observations, so that would be n. You can see that is a sum here of the variable 1, and this is a sum again. This is a symmetric matrix, meaning that this value will be the same as this, and this is the sum of x squared. Again, not that you need to remember that, but that's an idea of what x transpose x contains. Now, we need x transpose x, but we need the inverse of it. Okay? One thing you can do is, well, this is where it is going to be important that the determinant of that matrix is not equal to 0, because if it is equal to 0, then we would not be able to get that inverse. In other words, if the matrix has a singularity, then we are not able to compute the parameter estimates. Now let's check the determinant. I will do determinant of x transpose x and just check, and we see that this is equal to 50. So this determinant doesn't have any singularities. We can compute this. Okay, this step is not necessary. It's just I'm showing it to you so that you can see the process. It will become apparent why we need to understand about matrices that have singularities later down the road. But the determinant here is not 0. Okay. All right, so let's get the inverse now. So we know we can get an inverse, and let's call it inverse of x transpose x. Just calling it that, but this is an arbitrary naming. So I will do the solve function, but that gets me the x transpose x inverse. So this gets the inverse. All right, so I'm just gonna run that, and let me see what the inverse of that tells me. And again, we have that matrix is a 2 by 2. So if you have a matrix that is 2 by 2 and you get the inverse, and it's also going to be 2 by 2. Okay, so we got this part of the equation right here. Up to that, we need to get x transpose y. All right, so let's call it xty, and we're just gonna matrix multiply the transpose of x times, and again, remember that when you're going to multiply matrices, you have to use this, times y, and that's going to be the matrix x transpose y. And again, this is a vector because the matrix x is n number of observations by 2, and if I transpose that matrix, is going to be 2 by n, which in this case is by 5. So a 2 by 5 multiplied by a 5 by 1, it's going to get me a 2 by 1 vector, and that's what you see here. Okay. All right, so we have now the two parts. We have this part here, the inverse of x transpose x, and then x transpose y. Now we can calculate b. Again, you could have done that in a single step. You don't need to do that separately, but um, it's just showing you the process. So I will just do B is equal to the inverse of x transpose x multiplied, and again this is matrix multiplication, times x transpose y. And that's going to give me the parameter estimates. These are the two parameter estimates at the same time, 0 minus 0.1 and 0.7. Again, if you remember, these are the parameters that we should obtain. And then we can quickly check that using the linear model function. I can say, for instance, um, let's I mean, y is going to be the same thing, and let's say y, let's change it to sales is equal to, and then concatenate those values in there, 1, 1, 2, 2, and 4. And let's put advertising, and that's going to be 1, 2, 3, 4, and 5. Let's create the appliance data, which is going to be as a data frame of sales and advertising. So let me run that really quickly. Let's see what's the error here. Is that a character vector? Let's take a look at this really quick and see what we get. This is sales and this is advertising. Let's not do let's just do data.frame. That should work well. Okay. So now I have the appliance data set. So we have the y variable and the x variable. Now we can do the regression. So regression, let's call it regression 1, and then let's do the lm function here, and then let's do sales regressed by advertising using the data equal to appliance. Let's get the summary of that regression and also the ANOVA. Okay. All right, so we can see that the parameter estimates are also minus 0.1 and 0.7, which is exactly what we obtained using the parameter estimates here. Okay, so I just wanted to show you these because this is what goes on the background. On the background, this regression is obtained by using matrix notation. So R works by transforming everything that you put in into a matrix and then doing the calculations using this formula right here, using the fact that the beta vector can be obtained using x transpose x inverse x transpose y. The nice thing of these is that this works pretty well with any dimensions. So if you have a matrix that contains many dimensions, it still would work fine. So we'll take a look at another example using more than one dimension. But for now, let's just stop it there, and hopefully this is helpful.